Hello and good day. So today I would like to present about our product here. It's called the Biohybrid Engine Coolant. So my name is Associate Professor Devarajan from the Faculty of Engineering in the University of Malaysia Pahang. So you can contact me with this number 016-758-0946 or email at the email deba@ump.edu.my. So first of it would like to present to you our biohybrid engine coolant. Actually, we have inspired this material to become a new coolant because it is from a bio source and it is a renewable material. Uh, and as our findings is, the main novelty of this product is its of high thermal conductivity and can enhance the thermal conductivity by 25%. In sense, the rate of heat that is dissipated from the coolant is increased by 25%, and also the capacity of the heat that can be obtained or governed by the coolant is around 20%, and is also environmentally friendly. And these are the main usage of this coolant that we can use. We can use it for machining, we can use it for semiconductor cooling, and we can use it for power plant. But our main is for the automotive cooling because directly the engine is the one component that is being used very vastly in the world. So we are targeting the automotive coolant as our main function creator, and then we can apply our product into this highly used engines. Okay, so this is the PI that we have already submitted, and our patent is registered under East Coast Management, right? So we have already registered this patent, and the number is in the poster. So what is thermal contribution to the engine is that if there is too much heat in the engine, there is a wear formation in the piston, and also there is also a knocking phenomena that can occur. And as you know, a lot of thermal energy is being dissipated by the engine, and the more it can be dissipated, the more efficient the engine can become in terms of thermal usage. So if you look at engine, the main contributor for heat removal is from the radiator. So radiator reaches its limits for the modification, and somehow the radiator size is too big because of the amount of coolant that you need to use. So if you can find a way to make the coolant more efficient, we can find a way to reduce the size of the radiator and as such improve the vehicle design as a whole. So these are the types of coolant that already people have done, and people have done nanoparticle based nanofluids, and they also have done heat transfer enhancements for these two kind of nanofluids. Okay, so nanofluids is a new trend that people use to make a better coolant, okay, and modify the coolant so that it can become better and can be used for many usages. So for the heat transfer, if you can see, there is heat transfer and heat enhancements. So for these two things, we have seen a lot of literature saying that graphene and ethylene glycol has a way of reducing the heat transfer. And also some are using zinc as a main platform for the coolant. But in our case, we are adding a CNC, which is a cellulose nanocrystals, okay, and it has promised to give more enhancements, and we have done the rigorous testing on this material, and these are the supportive references for this our product. So when you talk about nanofluids itself, so there is a lot of methods that we can to use so that it can become a one product, and then we can make it a very stable, and also it is less sedimentation, and it can go into the long-term usage as a coolant itself. So the preparation of this one product is very crucial. Okay, so there is qualitative method and the quantitative method. In the qualitative method, we look at the sedimentation that occurs due to the products that we introduce. In our case, it's the graphene and the cellulose nanocrystals. And the quantitative method is the absorbance and the zeta potential and also the pH value that this product finally agrees to. So graphene itself, okay, is a very functional material. It can be used in the solar cells, cell batteries, and so on. It is very highly thermal conductive. So, and our main product here is the cellulose nanocrystal because it is dispersed in a higher concentration into the ethylene glycol. So, the cellulose nanocrystals are rigid and rod-like nanoparticles that usually prepared by acid hydrolysis, and it is used to from a plant base, and as exactly is a plant, and it can be taken from the plant, or where you can get it from viscous and viscous kind of format. And when it's the nanoparticles, it can transfer the heat very high because of its what you call this cell walls structures. So when there is a graphene and the CNC property combined, so we have a physical and morphology properties that we have to be looking at, and the hydrophilic and hydrophobic areas where we can see whether the particle will float or will sediment. Okay, so these are the aspects that we already analyzed. And as the viscous has high surface to volume, they can transfer more heat. Okay, so we are having also some modification for the chemical and also the distribution and surface functionalizations and also chemical and mechanical and thermal replications. The next one is the how this product is being prepared. So the preparation of this nanofluid comes from the stability validation first. So after we do a mixing of the ratio that we want, so concentration of 0.1 to 0.5 to 1.3, okay, as we go on, we will look at the qualitative method where we look at the stability of the product, and in this case the sedimentation is measured by the UV spectrometer. Okay, and after that we will do the thermophysical property measurements, in which the thermal conductivity, dynamic viscosity, density, and specific heat is measured. Okay, and then we test the product in a small scale radiator test rig, and also later we will also test in the real car itself. Okay, and after we test in the real car, we get the data collection and we analyze the data to find the final product. So to blend the CNC itself, we have because the CNC we get it from a gel form, and we get the concentration of 0.8, and we make it into flakes, and then we have to do a crushing method so that it becomes nanoparticles. Okay, and we have an initial concentration of 0.1 to 0.9 again, and in which here the graphene is added here, and the ultrasonic bath is done for the 2 hours with the help of the hot plate magnetic stirrer. So this you can see, this is the experimental setup that we have used. So this is a radiator setup. This radiator is from Produa Kancil. So it is a 1.0 liter, and it can has a bulk temperature and surface temperature and a flow rate, and we can also measure the pressure drop and the temperature distribution of this system. And we have a DAQ system that measures all the components and combines it into one file. So when we look at the stability, so when we add the cellulose plus with the graphene, so this is the color we get, and sedimentation is measured for the past 1 month. Okay, and this is the stability that we get. So we can get a stability of less than 30% if it is uh, in a long term. Okay, so the absorbance of the wave of the UV is, look at this, and we can say that it is stable by looking at the stable flat curve. So in terms of thermal conductivity, density, dynamic viscosity, and specific gravities, specific heat. So we can see we are measuring here, we are comparing to a standard which is called the ASHRAE standard. So in the ASHRAE standard, we compare Eg W, which is the ethylene glycol, which is the baseline fluid, with the one that we have done. So we can see from here that from our analysis, there is many concentrations, and from the concentration, the best one that we take is the, in our case right now, is the 0.5. Okay, but we are doing more rigorous testing on this to find whether the minimum and maximum heat capacity is obtained or not. So in terms of thermal conductivity itself, these are the many graphs that we get for the different concentration of the EG itself with the water before we introduce the particles inside. So when we use the particle enhancement, so we can get a minimum to a maximum enhancement of 28.9%, in which we found that the 25% is our best heat transfer conductivity for this product. Okay, for the viscosity, we can see that the viscosity is improving as we add the EG. As the temperature increases, the viscosity level increases, and as such, the pump will work better, and it has less resistance to the pump, and has also a way to reduce the pumping losses into the system of the radiator. So for the density itself, density also is slightly reducing as the temperature is increased, as more mixing is happening in the nanoscale. Same with the specific heat, amount of specific heat, you can see here, it is increasing a lot. Okay, and our 0.5 is having a lot of heat retainment into this coolant. So for the heat performance itself, you're looking at the Nusselt number, Reynolds number, and the heat transfer rate. So these are the readings that we get, and we can see that the Reynolds number, as it increases, the Nusselt number also increases. Same case for the heat transfer rate. This means that the product can transfer heat very fast, okay, uh, into the surrounding of the radiator fins. So in terms of friction factor itself, how much friction is occurring, the friction factor is reducing, and as such, this proves that the viscosity of the product is very good. Okay, when you look at the temperature profile, we can see a lot of yellowish and green colors in the middle of the radiator. This shows that when we add the nanofluid, okay, there is a lot of more green spots saying that the radiator is cooling faster, okay, and cooling more in the center of the radiator itself. And we have also done a corrosion test for this product. So when we did a corrosion test, we found out that the product has very good corrosion resistance. Okay, so in this case, you can see here 0.5 concentration has the lesser corrosive nature, and it will protect the radiator from any other reactions, so that the radiator can last longer. As a conclusion, we can say that dispersion of the graphene and the CNC crystals in the ethylene glycol and water produces a stable biohybrid nanofluid coolant. The thermal conductivity increases 0.492 at 30 degrees to 0.652 at 70 degrees. So this shows the amount of heat that can be obtained or released back to the environment from the coolant. The objective of the research was to determine the thermal influences and the viscosity of 7.6 and 0.5 volume concentration produces this product. And moreover, we have found out that the investigation on the effect of erosion on CNC coolant on the automotive radiator were also carried out, and this supports the credibility of the graphene CNC as a efficient radiator coolant. Okay, so we can say that the recommendations here we arrive after we looking at the base fluid, the temperature distributions, and the nanosubstance added to the radiator testing itself. So then only we can get the best coolant for this and the final product. So for the publication itself, these are the publications that we've already done and we've already published. Okay, so we have got WS impact factor of 0.6.35 published, and also there are many papers accepted and we are going to publish more once we have finalized this product again. So these are the list of references for this analysis that we have done. And we have our main companies that we are collaborating with, which is one of the from the USA, so focus applied testing. And we have done our collaborator from local, which is Gagasan Global, and we also have done with commercial car companies from BMW. This is our commercial link, and we hope that this product can be taken on seriously, and we can use it for the betterment of the vehicle itself. So currently we are applying more grants and more more commercialization activities, so that we can bring this product into a higher level. So with that, thank you very much, and hope this is serves as the presentation for this product. Thank you again.